Hello, everybody, and welcome once again to your physics channel. It's Physics Rich. Today, we are here to discuss the part 2 of the amazing Soorya-Veera problem. And in this problem, we had a problem. And the problem was Mr. Surya was sitting over here, Mr. Veera was sitting over here, and Surya had to throw an apple to Veera so that he had to use minimum possible speed to throw it so that the apple does not get dirty. And we found out that the speed was square root of gr upon 2, and it was in such way that when he throws, the apple goes in a way that it makes a tangent at this particular point on the cylinder. Now you see, guys, I have made the cylinder over here. So this is my cylinder, all right? Let me just show you. This is the cylinder that we are talking about, all right? This is the curvature of the cylinder. This is where Surya has thrown the apple. This is the direction. And we already know that he has thrown it with a velocity of square root of gr upon 2. But what we do not know is the angle with which he has thrown it. We know one more thing, that the apple, as it passes through over here, it makes one such angle alpha, which is equal to 30 degrees. We had calculated all of this in the previous video itself. If you haven't watched this video, please go and watch the previous video. Only then everything will make a lot of sense to you. So this alpha comes out to be 30 degrees, and because this is 30 degrees, we can see that this is a right angled triangle. And if this is a right angled triangle, then it obviously means that this angle must be 60 degrees. And if this angle is now 60 degrees, we can notice one very important thing in this triangle. This triangle turns out to be an equilateral triangle because already it is isosceles. R, R. Two sides are equal. Already it is isosceles. We already proved that this is 60 degrees, which means that now it is automatically proved that this angle is also 60 degrees. And if this angle is 60 degrees, then again it automatically gets proved that this whole angle is also 60 degrees. All right. And now that this entire angle has been proved to be 60 degrees, alpha has been proved to be 30 degrees, then again it means that this angle must also be equal to alpha. So we have found out that this hypothetical incline is inclined at alpha equals to 30 degrees with the horizontal. And this problem has now become a problem of projection on an incline. And for projection on an incline, we follow the regular kinematics. Regular kinematics as in the simple equations of s equals to ut plus half at square, v equals to u plus at, and v square equals to u square plus 2as. These kind of simple equations to deal with 2D kinematics problems. So one only problem here is that on this incline, there will be two components of acceleration. There will be ax, which is g sine alpha, and there is ay. This is g cos alpha. Please mind it, guys, that this illustration is on one of the more advanced type of illustrations. You require to know the basic theory of projection on incline. These formulas should not surprise you because they are all taught in the basic theory class. I will also add one basic theory class to projection on an incline so that it becomes easier for you to be acquainted with these formulas. Now, next thing, we have applied s equals to ut plus half at square along the x-axis, where the displacement along x, which is down the incline, is simply taken to be x. All right, and that becomes equals to ux t plus half ax t square. Ax is g sine alpha. This is ax, g sine alpha. And t is the time of flight, which I have found out using this method, which I have found out using y equals to 0 in the y equals to uyt minus half ayt square. If I put y equals to 0, I get t equals to this 2uy by ay. And then I can simply substitute the values of uy. Uy is nothing but the speed with which Surya has thrown, which is square root of gr by 2 times the sine of theta. Now, what is theta? Theta is the angle of projection, which is what we are actually trying to find. This is the thing that we are after in this problem. Okay, so this time becomes equals to 2 square root of 2r by 3g sine theta, and I would request you to pause the video over here and try to solve it right from this step to this step, because I've put cos 30, I'm sorry, equals to square root of 3 by 2, and after you put this, you get here. Moving on to the next part. Now, as I have found out the value of the time of flight, I will simply put this time in this equation, and this equation will then start to look somewhat like this. The distance from here to here is the range itself, okay, and because this is an equilateral triangle, this is equal to the radius r. This range and the radius, this radial distance become the same. So now I put x equals uxt. This is ux, okay, this is ux, this is t plus half ax, this is ax, and this is t squared. All right, this is t squared. Now when I solve this, again guys, I would request you, try to solve this by yourself. Do the calculation by yourself. If I solve this, all the g terms and all the r terms will get cancelled, and I will get a nice trigonometric format. And from solving this format, I will get theta equals to 60 degrees. Although I have solved it, you can pause the video and you can check your calculations if they are right or not. But I would request you, do it yourself. You will find a lot more confidence in yourself after doing it. Next thing is that we have already arrived to the answer, theta equals to 60 degrees. And that's it. We can close the discussion that, oh, we have found out the angle, theta equals to 60 degrees. The problem is solved. This theta is with the with this incline. Okay, this theta is with this incline. And this explains that as this theta is equals to 60 degrees, all right, if I form a horizontal from here, okay, and you see the Z shape, if this angle is alpha 30, this should also be 30. All right, this should also be 30. Now I have found this to be 30. I have found this to be 60. All right, which means that this angle has to be equal to 30 degrees. So if you report the answer of this problem as 30 degrees to the horizontal, you will get full marks. But my job here is to not just get you full marks. My job here is to make you really good at physics. Because it's physics rich. We have to be physics rich. Now, I will tell you some very beautiful methods to solve this problem. Well, one of my other students, he came up to me with a different approach. Let me tell you his approach once I tell you the real golden solution for this problem. Now, another student comes and tells me that, sir, we have found out the range formula. In our classes, we know that this is the range formula. Now, what I can do is that I can simply substitute the value of u, which is root over gr by 2. I can substitute the value of alpha, which is 30 degrees, and I will get cos alpha equals to root 3 upon 2. I will get sine alpha equals to 1 upon 2, and I can solve all of this, and I can simply do a little bit of trigonometry and get the answer from here as well. Now you see guys, I do not have a problem with this approach. I don't really have a problem with this approach. This approach and the previous approach are, well, maybe we can say that this is slightly better, okay? But it's not the best approach. You can solve this using the standard range formula, but then again, it will not be the best approach. Guys, hold on to your breath. I will slowly move on and tell you the best way to solve this problem. We have the range formula, but here's the thing, guys. Let me remind you of this concept that the maximum range comes out when you differentiate this equation, put equal to 0, theta comes out to be pi by 2 minus alpha by 2. We have done all of this in our regular classes. And the range then comes out to be this value. All right, the range then comes out to be this value. Now you see, for projection down the incline, the minus is used, and for projection up the incline, the plus is used. So what are we going to use? We are projecting down the incline, so we are going to use the negative sign. So let's use the negative sign once. And you will see some strange coincidence. And that strange coincidence is actually not really a coincidence. You know why? Because if you put alpha equals to 30 degrees, you get sine alpha equals to 1 upon 2. 1 minus 1 upon 2 is just 1 upon 2. And you get u square equals to rg upon 2. Is that a coincidence? Really? So guys, let's come back to the original concept of maximum range. Remember when I told you that if I have a ground and on this ground I have this range, okay, I have this range. What I want is to throw a velocity, throw a projectile with a velocity u so that it reaches this range. Then what did you say? Sir, throw it at 45 degrees, right? You said that if I have a speed u, the maximum range comes out as 45 degree at 45 degrees, correct? But the converse of this problem is that if I already have the range, then at 45 degrees, the speed which covers this range is the minimum speed at which you can cover that range. What was the original problem? Surya was supposed to throw it at the minimum speed. Okay, you see the connection? At the minimum speed, u square equals to rg upon 2 is actually the minimum speed, which we are getting if we put the range equal to r. Now you see that the apple is thrown at the speed which corresponds to the minimum speed required to cover a range of r on a plane inclined at alpha equals to 30. That solves the problem. Do you know why? See, this angle, okay, this angle, this is the angle at which you get the minimum speed for that range. The angle of projection for such a specific case comes out to be theta equals to pi by 2 minus alpha by 2. This is a very special angle. Okay, tell me, this is 90 degrees. Where is the bisector of this? You will say, sir, it's right in the middle. It's exactly in the middle. Oh, I seem to have a difficulty in holding this pen, but I hope you can imagine that if I have this 90 degrees, then the bisector will be here. Okay, the bisector will be here. What am I looking for? I am looking for the bisector between the incline and the vertical. This is my incline. This is my incline. This is my vertical. All right? My answer is exactly on the bisector. Let's go back to the original geometry. Now we know all we have to do is to find the bisector. Sure, why not? Let's go. So you see guys, this angle is 60. What is this angle? It will be 120, right? What is the half of 120? The half of 120 is 60. There you go. Your answer is set. So guys, such a beautiful problem can be solved in one go if you simply know that you are trying to solve a minimization problem. All right. And this minimization is happening at the angle bisector of this angle. This angle is 120 and the angle bisector is at 60 degrees. And there you go. That's the solution to this problem. Now, guys, I cannot just simply leave you so easily, can I? You wouldn't be physics rich if you were to stop thinking about physics. So let me make you think a little bit more. Now you see, guys, Mr. Veera and Mr. Surya are standing on either side of the physics rich logo. Now this logo is a circle. As you have noticed, this logo is a circle. Again, the same problem occurs. Mr. Surya is eating the apple, Mr. Veera wants the apple, and Mr. Veera yells at Mr. Surya, Yenakku apple venum. And Surya, being Surya, throws the apple in such a way that it goes like this and reaches Veera. But guys, I'm sure you are familiar with Mr. Surya by now. He doesn't like to do a lot of things. He likes to do things that do not require a lot of energy, so he will throw at a minimum speed. Now my question is, at what speed should Surya throw the apple so that it reaches Veera on the either side? Think about this problem and I will upload the solution to this in the next video. Until then, get physics rich.